You're plugged into the wall, pushing through a project, and a sudden power surge hits. There's a tiny pop, and your laptop shuts down entirely. You hold your breath, hit the power button, and it boots right back up. You open a web browser, check your email, and everything seems completely fine. But underneath the keyboard, a single MP8496 IC chip took the brunt of that surge and died. This leaves you with a difficult question. Is this machine actually safe to keep using, or is it secretly destroying itself from the inside out every time you turn it on? The short answer is that your laptop is lying to you. It might be running, but it is functioning in a compromised state, hiding a critical hardware loss that will eventually exact a severe toll. This image shows a motherboard's Voltage Regulator Module, or VRM. It takes high voltage from your wall and steps it down into clean, low voltage for your CPU. Notice the labeled physical components, the MOSFETs, inductors, and controllers. Modern laptops demand a lot of power. To deliver it safely, they use a multi-phase design. This means they divide the massive electrical current required by the CPU across several identical VRM pathways. This diagram compares a healthy system to a damaged one. A healthy three-phase setup shares thermal load evenly. Losing one phase forces the electrical load into surviving pathways. The motherboard instantly passes this orphaned load, and the burden jumps from 33 to 50. This shows how individual phases pulse on and off to deliver power. With fewer phases available, the remaining ones have to pulse harder and far more frequently to stack up the required total current. This kicks off a positive thermal feedback loop. As these surviving MOSFETs run hotter, their electrical resistance increases. That inefficiency means they generate even more heat to deliver the same amount of power. You will feel this immediately. To prevent a literal fire, the VRM will aggressively cut the frequency and voltage sent to your CPU. Your game will suffer frame drops, and your software will stutter as the system violently throttles. If you keep pushing it, you are running those surviving chips and the nearby capacitors well past their maximum thermal limits for hours at a time. Choosing to do nothing might save you money today, but if you demand heavy performance from a broken board, you are guaranteeing a total, unrecoverable cascade failure in the near future. The alternative to that cascade failure is opening the machine up, physically removing the blown IC chip, and attaching a new one. This requires specialized equipment. You need board-level schematics to locate the exact traces, and you need a hot air rework station to melt the factory solder without baking the rest of the motherboard. Placing the new chip onto the existing pads requires microscopic precision. We are talking about millimeter-scale alignments done by hand. The penalty for missing that alignment is absolute. If you accidentally bridge two adjacent pads with a speck of solder, you will send fatal voltage directly into the CPU the second you press the power button. Replacing an IC is high-risk surgical intervention. One slip of the hand turns a hobbled laptop into permanent electronic garbage. There is also a hidden risk here. Just accessing the VRMs means removing the main heatsink, which permanently destroys the factory thermal paste and putty. Let's look at the cross-section of a motherboard. The components, the VRMs, VRAM, and CPU, are not perfectly level. Differently sized gaps between the chips and heatsink must be filled. Reapplying this putty is a balancing act. Too much prevents the heatsink from touching the CPU. Too little, and the VRMs overheat. Even if your micro-soldering is flawless, your system will still fail if your reassembly and thermal putty application isn't mathematically precise. To figure out your next move, we map your hardware reality to your daily workflow. This chart plots the effort versus impact of your two primary options. We can translate this directly into a decision tree based on how you actually use your computer. If you are a pragmatic user who mostly runs Excel and web browsers, your CPU rarely demands peak wattage. The two surviving power phases can likely handle that light load without dangerously overheating. To protect the machine, you should download software to undervolt the CPU, or simply limit the maximum processor state in your Windows power settings. This ensures the system never attempts to draw spike currents. But if you demand full performance for gaming or rendering, you are out of time. The surviving VRMs will hit 100 degrees Celsius and die. Ignoring the problem is no longer an option. A light user can stretch a few more years out of a broken board. A heavy user cannot. If you are thinking about repairing this yourself, don't. Unless you already own digital calipers, a hot air station, and have real micro-soldering experience, the odds of destroying the board are too high. You can send the laptop to a professional board-level technician, but you need to weigh their hourly labor rate against the cost of just buying a replacement motherboard entirely. Whatever you decide, understand that you cannot push a compromised board to its limits. Trying to do so will cost you the entire laptop. You either need to replace the hardware or permanently downgrade your usage habits. There is no magic, risk-free fix.